In this video, we are going to understand one of the most important ideas in machine learning evaluation, the difference between accuracy, precision, and recall. We will use a fraud detection example because it makes the problem very real. By the end, you will see why a model that looks amazing with 99% accuracy can still be practically useless if it does not catch the rare class that actually matters. Imagine you build a fraud detection model and it reports 99.4% accuracy. At first glance, that sounds fantastic.
The dashboard turns green, everyone feels confident, and the model looks production ready.
But then someone asks one uncomfortable question. How much fraud did it actually catch? The answer is 0. This is the accuracy trap. The model is correct most of the time only because fraud is rare, but it fails on the thing we actually care about. Fraud detection is a classic imbalanced classification problem. In this example, we simulate 20,000 transactions, but only 0.6% of them are fraudulent. That means just 120 transactions are fraud, while 19,880 are legitimate. When the data is this skewed, a model can look very accurate by simply predicting the majority class. But from a business perspective, the minority class is exactly the class we care about. Accuracy answers a very simple question. How often was the model correct overall? That is useful in many situations, especially when classes are reasonably balanced and mistakes have similar cost. But in fraud detection, the data is not balanced and the mistake costs are not equal. Missing a fraud transaction is not the same as approving a normal one, so accuracy is not wrong, but it is incomplete. It can make a bad model look impressive. Let us create the laziest possible fraud model. This model does not learn anything. It does not look at the transaction amount, time of day, or behavior patterns. It simply predicts not fraud for every transaction. It sounds ridiculous, and it is ridiculous, but it is also a very useful baseline because it reveals how dangerous accuracy can be on imbalanced data. Here is the shocking result. The lazy model achieves about 99.4% accuracy. Why? Because most transactions really are legitimate. But precision is 0 because the model never raises a fraud alert. Recall is 0 because it catches none of the actual fraud cases. The F1 score is also 0. This is the key lesson. The model wins the accuracy game but completely fails the fraud detection problem. This chart shows the accuracy trap clearly. If we only look at accuracy, the lazy model appears to win. But when we look at precision, recall, and F1 score, the story changes completely. The real model has lower accuracy, but it catches a large portion of actual fraud. In fraud detection, the business value is not in being right about the easy normal transactions. The value is in finding the rare, risky ones. Precision tells us how trustworthy our fraud alerts are. If the model flags a transaction as fraud, precision asks how often that alert is actually correct. High precision means fewer false alarms and less wasted investigation effort. Low precision means normal customers may be blocked and fraud analysts may spend too much time looking at bad alerts. In simple terms, precision is about alert quality. Recall tells us how much actual fraud the model successfully detects. If there are 100 real fraud transactions and the model catches 80 of them, recall is 80%. This is the metric that answers the operational question. Did we catch the fraud or did the money walk out the door? In rare event detection, recall is often extremely important because the missed cases can carry direct business cost. The confusion matrix helps us connect model metrics to business outcomes. True negatives are normal transactions correctly allowed. False positives are legitimate customers incorrectly flagged as fraud, which can create friction and support calls. False negatives are real fraud cases that the model misses, and those are usually expensive. True positives are the cases where fraud is correctly detected. Once you see the confusion matrix this way, the metrics become much more practical.
Now, we replace the lazy rule with an actual logistic regression model.
The model looks at useful transaction features like amount, hour of day, and recent transaction velocity. We also use class weight balanced, which tells the model that the rare fraud class deserves more attention. This does not magically solve fraud detection, but it prevents the model from casually ignoring the minority class. This is where the lesson becomes clear. The lazy model gets 99.4% accuracy, while the real model gets around 85.3% accuracy. If we stop there, we might choose the wrong model. But recall tells the real story. The lazy model catches zero fraud. The real model catches roughly 78% of fraud. So the model with lower accuracy is actually far more useful for the business. A classifier often gives us a probability score. The threshold converts that score into a decision: fraud or not fraud. When we lower the threshold, we flag more transactions, which usually increases recall but reduces precision because we create more false alarms. When we raise the threshold, we become more selective, which may improve precision but reduce recall. This is the precision recall trade-off, and it is one of the most important ideas in operational machine learning. There is no mathematically perfect threshold that works for every business. The right threshold depends on the cost of missing fraud, the cost of blocking genuine customers, and the capacity of the fraud operations team. A bank may choose a different threshold for a small card transaction compared with a large international wire transfer. This is why threshold tuning is not only a data science activity. It is a business and risk decision. Here is the cheat sheet. Accuracy asks how often the model is correct overall. Precision asks how reliable the positive predictions are. Recall asks how much of the real positive class we captured. F1 score provides one combined view of precision and recall, but even F1 should be interpreted in context. For imbalanced problems like fraud detection, disease screening, defect detection, or churn prediction, accuracy alone is not enough. The final takeaway is simple. A model that looks good on a dashboard is not always good in the real world. In imbalanced problems like fraud detection, accuracy can be dangerously misleading. So whenever you evaluate a machine learning model, need to ask which mistakes matter most and whether the metric reflects the real business problem. Thanks for watching, and if you found this useful, subscribe for more machine learning, MLOps, and data engineering solutions.